Hello everyone. If you recall, in the last lecture we started discussing circuits where the input or the kind of voltage or current or source of energy that is connected to the circuit is a sinusoidal function. And once we actually wrote all the equation for the components and KCL for this simple circuit, for example, or for that matter for any circuit with linear components that we have studied so far. With that, what I mean are linear resistors, linear inductors, linear capacitors, linear transformers, any of those kind of components that we have discussed so far. If you put them in a network and then connect sources that are of sinusoidal family, then when you try to analyze the circuit and write the equation for the circuit, once you start solving that set of equations, you're going to end up getting a differential equation, the result of which is going to have two different components. One is the transient component with an exponential function that kind of dies out, generally speaking, and the other component that is an alternating voltage or alternating signal or current. And generally speaking, a lot of times the electrical engineers are interested in that steady state that is not going to go away, as opposed to that transient component. And then we looked at that transient, the steady state component, and we noticed that no matter what current or voltage we write in that linear circuit, if the input signal is an alternating sinusoidal signal, then all these voltages and currents in that circuit are going to end up having the same format. In other words, they're going to be sinusoidal functions with the same frequency, and the only thing that is going to be different than what you have in the input is either the amplitude or phase or both. So now this time or from now on, we're going to try to kind of start getting smart about doing our analysis, and we're going to try to find ways to skip doing differential equations. Really, math is the most complicated part of doing the analysis, and if we can do things that helps us simplify that process, we can basically speed up the process of doing circuit analysis, and we can get intuitive understanding of what is going on in the circuit faster. So now, what does that mean for this simple, like this, what I just explained? So we said we have a source of voltage that is in the sinusoidal form with the amplitude of Vm, frequency or angular frequency of omega, and a phase of phi. Now, that means that, for example, the current that is in this circuit, I1t, is going to also have an amplitude of Im with a cosine omega t that is then going to end up being the same frequency plus a different phase. I'm going to call it phi 1, right? And then V1t also, for that matter, is going to have another amplitude. Let's actually call that I1. So, and this one is going to have an amplitude V1 cosine omega t plus another phi 2. And this format just follows that format, as you can see. What's going to change is the amplitude of the signal that we're looking for, and these are the only two signal. There's a voltage here, voltage there for the two nodes. That's assumed ground, and there's one current that is going into this loop. So any signal in that circuit, therefore, is going to have this same format of an amplitude, a sinusoidal function with a frequency that matches the frequency of the input, and a phase that may or may not be different than what the input is, depending on what the circuit is. So if I can find a way to quickly calculate these values, in other words, the magnitudes and the phases in the circuit, without doing too much of a math, in other words, differential equation, then I'm speeding up the process of circuit analysis, and that's what we're going to try to do in today and most likely the next lecture. So here I'm introducing this mathematical equation. It's also called the Eulers equation, a very beautiful and useful equation that kind of relates two seemingly different concepts to each other. So on one end you have E, and that is actually to the power of j theta, and j is a square root of -1. So it's the base for the imaginary numbers, right? And on the other hand, you have cosine and sine in this specific format. One way that you can kind of try to make sense of this and kind of intuitively understand what's going on. You can imagine that in the field or space, 2D space of complex numbers, we have two axes, x-axis, let's say those are the real numbers, and the y-axis are the imaginary numbers. Let's put a circle with a radius of 1 in this space, the 2D space. Now, as you can define a vector that kind of moves on the perimeter of this circle, right? As it moves from the positive portion of the x-axis, you're going to have an angle that as this vector moves, this angle changes and increases from 0, goes to 2 pi here, to pi over 2 here, pi, 3 pi over 2, and then finally goes back to 2 pi or 0 again. Now, this vector, if you want to write it in the form of a vector in the x direction plus a vector in y direction, you can clearly see that the projection of this vector on the x-axis is actually equal to the magnitude of this vector times the cosine of this angle. So this angle, in other words, this vector is the magnitude of this, which now we know that the magnitude is 1 because the magnitude is equal to the magnitude of the vector, which obviously is 1. It's moving on a circle with the radius of 1. So this vector right here on the real part would be cosine of theta. Now, similar to that, if you want to calculate that, this is actually j sine of theta. Okay, so j because it's in the imaginary direction, and then sine of theta. So now you add these two up, you get this vector, and that's actually exactly that equation. Okay, so in other words, if you calculate the magnitude of this vector that is in the imaginary or the complex numbers space, the magnitude actually is going to end up being 1. And if you calculate the magnitude of this, is cosine to the power of 2 plus sine to the power of 2, and we know that that's equal to 1. That's quite a common equation, or typical or important and known equation in mathematics, that the cosine to the power of 2 and sine plus sine to the power of 2 is equal to 1. So this is kind of a way, at least for me, to relate to this equation and understand what is going on. Now, we're going to take advantage of this equation and do something here as I'm about to explain. Okay, so we're going to define this concept that is called phasors. The general form of a signal, sinusoidal signal, we said is an amplitude multiplied by cosine of omega, angular frequency, times time plus a phase. Okay? I know that I'm now anticipating that when I'm looking for solution for my circuit, this component, I don't need to calculate the frequency. In other words, this component, the omega t component, is going to be repeated for all of the unknowns in the circuit, all the currents and voltages and signals in the circuit. Therefore, I don't need to spend any time trying to figure that out. All I need to do is the magnitude and the phase. So therefore, we're going to actually define a transformation that kind of preserves, it moves this signal, transforms this signal, or transforms this function from a domain where omega t exists, or in other words, time exists, to a domain where the time doesn't exist anymore, because I actually don't need to keep track of time, because the component of the signal that changes with time is known to me. I already know that. And that transformation is called the Phasor transformation. And this is quite typical in math to do transformation. Basically, you take values from one field and move them to a different field, because these different fields have different properties, and once you have a certain need for a certain property that doesn't exist in this field, then you move it to the, or you don't want that specific property. For example, in this case, there's the time dependency, and when I do the Phasor transformation, I get rid of that time dependency, because I don't care about it and I want to simplify my calculation. So with the Phasor transformation, you move it to a different domain, and in this domain, let me follow. So Vm turns into Vm e to the j phi with the Phasor transformation. So I'm going to repeat and write the equation like this. So Phasor transformation of a general signal, sinusoidal signal, cosine omega, Vm cosine omega t plus phi is Vm magnitude E j the phase. Now you can clearly see that on the other side of this transformation, the information about the magnitude is preserved. So magnitude is there. The information about the phase is preserved. The phase is there, but the time dependency is no longer showing up here. Now, if I use this transformation now to the equations that I had for this circuit, I'm going to transform all those equations to a domain where there is no time dependency. And you're going to see later on, most likely in the next lecture, that that's going to simplify the circuit quite a lot for these specific kind of signals, to an extent that I no longer need to do differential equations. Keep in mind, this is only true if all I'm interested in knowing is the steady state of the component of the response, and therefore I'm looking at the circuit in the long term, at which point the transients are gone. All the exponential, decaying exponential equations are almost zero, and therefore my steady state is the dominant portion of the result. Okay, so let's practice moving, because you can actually take now any voltage or current signal and turn it into, transfer it to the Phasor domain. You can actually do the reverse. You can take any of the Phasor domain representation of a signal and bring it back to the time domain. Now, you have to keep in mind that for that transformation, you have to know what this frequency is, right? So because here you don't see the frequency, so that frequency has to be given, or then you can bring it back. Now, let's practice that with a few examples to make sure that we understand this, and then we're going to, in the next lecture, we're going to start using this Phasor equation and apply it to equations for the circuit, in other words, equations for components. So we take equations for different components that we have discussed so far, specifically resistors and inductors and capacitors, and see how those equations are going to be represented in the phasor domain, and you will see how that's going to simplify our math. So let's do a few examples. I'm going to try to do them maybe here without removing anything. So let's say I am looking for I'm looking at a voltage signal that is 2 cosine of 2 pi times 60 times t minus 30 degrees. Okay, now I want to take this signal and then transform it into phasor domain. So you can see the phasor domain, the phasor transformation down here. So as you know, this signal, what it means is that the angular frequency is 2 pi times 60. So the frequency in hertz, or normal frequency f, is actually 60 hertz. And it has a phase of minus 30 degrees. Now, the presentation becomes 2, so we, in the phasor domain, we know that the magnitude is going to be preserved. There is no time dependency. This is gone. E to the j, now this is the phase, minus 30 degrees. So minus 30 degrees. Now if you want to turn this into angular frequency, which is actually not a bad idea to be consistent, because that's what we have done here. This becomes, so that's pi over 6, so that would be pi over 6. Okay, so this is the phasor representation. Now, if I wanted, let's imagine that I was given this phasor and now I wanted to do the reverse of that. If that was the case, then I had to be given what the frequency of this signal is, because as you can see in the phasor domain, there is no information about the frequency or time. Keep in mind, time and frequency, we already know they are basically the same thing, because dependency on time and frequency, because the frequency tells you how many times per second something repeats, right? In other words, frequency is 1 over t period in seconds. So with this, I had to be given a frequency, and let's say I've been given a frequency f of 60 hertz. So when you go back to the time domain, again, the magnitude is preserved, the signal is in the form of cosine, and then omega, basically equivalent to 60 hertz, is 2 pi times 60. So you put that here, 2 pi times 60 times t, the time, and then the phase, and you can see the phase right there, minus pi over 6. So one time you go from the time domain to phasor domain, and if you were given the phasor domain with a frequency, you can go back to time domain now. So with that, I think we're ready to start doing phasor transformation on the equations associated with the circuit, resistors, inductors, and capacitors, and that's the objective of the next lecture that you're going to see next time. Thank you. Appreciate it.